tried 10 and 11 on your own now, you should really pause the video and do it yourself first. I'm just going to go over it as if you have done it, and it is really good practice. So if you have done it, let's review. When you're solving an integral, the first thing you want to do is find the antiderivative. So that's going to be negative t cubed plus 2t squared minus t from 2 to x. Plug in x, you get negative x cubed plus 2x squared minus x minus negative 2 to the third plus 2 times 2 squared minus 2. And that just becomes negative x cubed plus 2x squared minus x. And then negative 8 plus 8 cancels, and you just get minus negative 2, so plus 2. And then this one says find the derivative of the integral from 2 to the x of blah, 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 blah. Hey, I already just solved this whole thing, right? So let's just take the derivative of my answer. Right? You did this, and we always work inside out. So you did the inside part. Now we're just taking the derivative. We get negative 3x squared plus 4x minus 1. Hey, what do we notice? Isn't that just the original function? But instead of t's, it has x's plugged in. So that's what FTC part 2 basically tells us, is if you take the derivative of an integral, they kind of cancel each other out. They don't like totally cancel each other. We're not left with t's. But if you think about the steps that you're doing, you're finding the antiderivative and then you're taking the derivative. Well, if you find the antiderivative and then take the derivative, what do you end up with? The original function. So the derivative of the integral from a to x of f of t dt is f of x. And then if you take the derivative of the integral from x to a, the only thing I've changed here is the bounds. Well, if I change the bounds, that's just going to be negative the answer if my bounds were switched. So for number 12 and 13, now that you know the rule, as long as you understand that I'm taking the antiderivative and then I am taking the derivative. So think about, again, you're taking the antiderivative, you plug in x, you take the antiderivative, you plug in 45.7. Once you take the derivative of the 45.7 part, the derivative of any constant is 0. So when I plug in 45.7 into my antiderivative and then I take the derivative, that part goes away. So the only part that remains is going to be negative 3e to the 5x minus 6 cosine cubed of x plus 8x. And that's it. That's my answer. I don't have to show any work. I just fundamentally understand that I'm plugging in the bounds into my antiderivative. And then when I take the derivative of my antiderivative, I end up with the original function. And then for this one, likewise, if I plug in negative pi, that negative pi is just a constant. If I plug that in, I get into my antiderivative. I would get some sort of constant. And then when I take the derivative of my antiderivative with negative pi plugged in, that part goes away. The only part that is going to remain is my lower bound part. And remember, when you plug in the lower bound, you are subtracting. So it's going to be negative 2 to the x plus 6 log of x squared plus 81.2 x to the 6th. So once you understand what it is that you're doing here and you see the connection, you don't really have to show any work as long as you understand derivative, antiderivative, they kind of undo each other. So not a lot of work to show here.